Hi everyone, thank you for attending this presentation for ITSC. My name is Zhou Zhao from University of California, Riverside, and I'll be presenting today for our work collaborating closely with Honda Research Institute. Here I'll be detailing our research of connected vehicle-based advanced detection of slowdown events on freeways. I'll first describe the problem that we want to solve and then introduce the methodology. Next, I'll elaborate on the simulation study and the key findings from the simulation result. And finally, I'll discuss the potential directions of the research in the future. The objective of this study is to explore effective algorithms for the advanced detection of slowdown events by taking full advantage of vehicle-to-vehicle communications. There could be two different perspectives to tackle this problem, macroscopic and macroscopic perspectives. And each perspective has its pros and cons as shown in this figure. From the macroscopic perspective, the longitudinal dynamics of the vehicle are modeled by car following or driving behavior models. Therefore, the detailed kinematics is considered, and the short-term prediction can be very accurate. However, due to the stochastic nature of the human drivers, the long-term prediction can be relatively unreliable. On the contrary, slowdown events are depicted by shockwave of the traffic from the macroscopic perspective. This may lose certain level of resolution compared to the car following model-based method. However, because it captures the oscillation propagation property of the traffic, usually it can provide better result for long-term prediction. To formulate the problem, a host vehicle's bird's-eye view traveling along the same line over a consecutive time window can be stitched together as shown in this figure. In this space-time diagram, the red solid curve represent the trajectory of the host vehicle, and the yellow dashed curve represent the maximum communication range of the host vehicle along its trajectory. The shaded area under the yellow dashed curve, in principle, denote the maximum spatial temporal region or information available region, where all the possible downstream traffic information can be available to the host vehicle up to the time instant to make real-time decision. Based on this information, the host vehicle might be able to detect imminent downstream shock waves that may result in its slowdown maneuvers. Interestingly, if the host vehicle travels fast, the information available region, or IAR, is small, or the maximum backtracking duration is short. If the host vehicle speed is slow, the IAR is large, or the maximum backtracking duration is long. In addition, if the roadway is divided into cells and the backtracking time window is selected, then the area of information available region that can be covered by the horizontal bars will depend on the size of the cell and the length of the backtracking time window. By varying these parameters with the host vehicle speed, better coverage of IAR would be expected, and potentially more information would be available for the host vehicle to support decision-making in real time. In this study, we developed and evaluated two algorithms for the detection of slowdown or shockwave events. The first proposed metric to identify slowdown event is called cell-based average deceleration, or CAD. As shown in the right-hand figure, the entire road network is first discretized into cells on a lane-by-lane basis. A host vehicle continuously monitors its downstream traffic state at the cell level within a specific communication range. Calculating the average deceleration for each individual cell according to the equation in this slide. For cell ij, we calculate the average speed among all vehicles in the cell, and then the CAD is defined by the changing rate of current average speed with the previous average speed with predefined time interval. Once CAD of each cell is calculated, a flag raising strategy is applied if CAD satisfies the condition. The second proposed approach is enlightened by Alpha et al., which utilizes the vehicle distribution information to identify the slowdown event along the road segment. We have modified this method for real-time slowdown event prediction purpose with the following 4 steps. First, similar to the approach 1, we divide the road segment into cells with the user-defined length. Then we calculate the average speed of each vehicle along each road segment at a lane level over a user-defined time interval. Next, we calculate the speed standard deviation, or SSD, of the average speed of all the individual vehicles for each cell at each time step. And finally, a flag raising strategy is applied when SSD satisfies the condition. This slide shows the flag raising strategies for both CAD and SSD methods. There are 3 major steps in this process. First, raising flag if any of the valid cell satisfies the condition for successive edge steps. More specifically, at each time step, the host vehicle may have prediction result from multiple cells, where the flag is raised if the predefined thresholds are satisfied. Then, the result of all cells are combined using OR logic. Since the prediction signal can be fluctuant due to the randomness of the driving behaviors, change of the valid cells, and change of the vehicles in the cells, it is necessary to smooth the signal and make them robust enough for performance evaluation. Therefore, we group any successive prediction sequences with 2 small time intervals into one detection, and remove any flag raising event that has too small duration. We use confusion matrix for performance evaluation. As shown in the right-hand figure, each row of the matrix represents the instances in the predicted class, while each column represents the instance in the actual class. The 4 entries of the confusion matrix are true positive, true negative, false positive, and false negative. For event-based performance analysis, the matrix can fill out by simply counting the number of each event. In this case, however, to measure the performance of the proposed slowdown prediction method, the definition of the predicted class needs to be modified because the non-slowdown event incidents are not counted. Therefore, we use rate rather than number to quantify the predicted class. This slide shows a more detailed description. For each slowdown event, the onset time of the slowdown are marked in red dot in the figure. We define a lookback time window marked in blue, denoting the interval of valid prediction. Then the true positive event is defined as the earliest prediction within the time window. Similarly, the number of false negative events count the slowdown event that without prediction flag in the corresponding time window. As to the false positive and true negative, the definitions are different, as it is hard to define the number of non-slowdown events. Therefore, false positive rate is defined as the time duration of flag rising up outside the time window divided by the overall non-slowdown time duration. And true negative rate is defined as the time duration without rising flag and outside the time window, divided by the overall non-slowdown time duration. To investigate the performance, we have coded a real-world network in PTV Vism, a macroscopic traffic simulation platform, with up-to-date roadway geometry as shown in the figure. More specifically, the network is a selected segment of US 33 East in Ohio, which is a 5-mile-long road, stretches with 2 to 5 lanes. The off-ramp 3 and 4 are the road to I-270 North and I-270 South, respectively. Between on-ramp 2 and off-ramp 3 and 4, there are 4 lanes in total, and the traffic volume is very high. Also, when the traffic volume from upstream is high, the on-ramp 1 would be another bottleneck area, where the merging vehicles from on-ramp 1 slow down the mainland traffic in both left and right lanes. The input volume, which is considered as a moderate demand scenario, and the static vehicle routing decision have been carefully calibrated to investigate how the prediction performance of the proposed method would vary in different traffic demand. We select another traffic input volume as a high demand scenario. The volume of each tested scenario is shown in the table. To investigate how the prediction performance would vary in different CV penetration rate, 4 levels of CV penetration rate are simulated. To have more speed variation samples, during the 30-minute simulation, 4 artificial slowdown incidents have been generated using the COM interface. Other than control speed of the slowdown vehicle directly, the research team codes the script using the COM interface to change the desired speed of the target vehicle to achieve more realistic incidents. As a result, the target vehicle slowed down smoothly, governed by the driving model in the PTV Vism, and other vehicles respond to the target vehicles accordingly. Besides the condition to identify the slowdown event, the selection of algorithm parameters may significantly impact the system performance. The choice of these parameters may balance the sensitivity, accuracy, and the robustness of the algorithm. In this study, we apply a trial and error approach based on observations from the simulation result, and the parameters used for this study are shown in this slide. The table in this slide summarizes the overall simulation results. Regarding different traffic demand and penetration rate of the connected vehicles, the proposed algorithm's performance may be degraded in low penetration rate and moderate traffic demand, mainly due to the lack of available information for robust prediction of slowdown events. At 100% CV penetration rate, both CAD and SSD approach have very comparative performance, where the accuracy is about 70%. With the decrease of the CV penetration rate, the prediction performance of both CAD and SSD decreases accordingly due to the less information being available. Both CAD and SSD becomes less sensitive to the slowdown events, which can be verified by the decreased trend of true positive rate and the increased trend of false positive rate. When the CV penetration rate is as low as 25%, the true positive rate for both CAD and SSD are less than or equal to 0.5, which make the prediction unreliable. Compared with SSD, CAD is more sensitive because it consistently has larger true positive rate over different scenarios. However, due to its higher sensitivity, CAD also has more false positive rate, which reduces the prediction accuracy. In terms of the detection time, CAD typically has an earlier prediction compared to SSD. When the traffic becomes less congested, the number of vehicles in the valid cell and even the number of valid cells decrease significantly. Therefore, the prediction performance at moderate demand is worse than higher demand, with the same CV penetration rate. In particular, CAD is much more reliable than SSD during the moderate traffic condition. It should be noted that all the conclusions above are based on the simulation scenarios, and the robustness of the findings need further investigation. The proposed approaches are governed by a number of predefined thresholds and parameters, which can largely impact the performance of the prediction. In this project, such parameters are chosen based on the observations from a limited set of collected data. Therefore, one potential research direction is to find a systematic way to leverage the power of data-driven methods to find an optimal set of parameters, or the best schema to select these parameters. It is admitted that a single set of parameters may not be able to cover all the traffic scenarios. For example, the optimal CAD threshold and the cell size in low-speed scenarios might be different from those in high-speed scenarios, as is explained in the bird's-eye view figure in the previous slide. Therefore, adaptive method that can adjust the parameters according to the contemporary situation is worth further investigation. Finally, end-to-end learning techniques using deep neural network is a promising candidate method for further exploration. This may help not only the identification of the ground truth event, but also the detection and prediction of this event. By leveraging the macroscopic traffic simulation software such as PTVism, a large amount of data can be easily generated for the learning purpose. Nevertheless, how to transfer the learning result from the simulation environment to the real-world situation is also an interesting topic. Thank you again for your time. If you have any questions or comments, please feel free to contact us.